A neutron star packs the mass of our Sun into a sphere barely 20 kilometers wide. Inside, matter is crushed to extremes we can hardly imagine. But what really happens within such a cosmic furnace? In this 2-hour journey, we'll dive into the science of nature's strangest stars. Please like, subscribe and share, and tell us in the comments what part of neutron stars fascinates you most. Thank you for being here. Now let's begin. A neutron star exists as one of the densest objects in the universe, formed after the gravitational collapse of a massive star's core. To understand what happens inside it is useful first to examine what surrounds the star, because the outer environment controls how energy and information leave the surface. This environment consists of a very thin atmosphere pressed against a rigid surface and a structured magnetosphere that extends outward along magnetic field lines. The atmosphere is measured in mere centimeters to meters in thickness, yet gravity here is 1 billion times stronger than on Earth. In such gravity, atoms do not remain intact. Electrons are stripped from nuclei, and matter exists as an ionized plasma that is tied to the surface by the enormous gravitational pull. Because gravity bends light radiation that leaves the surface follows curved paths, so the star appears slightly larger than its true geometric outline. Photons also climb out of a deep gravitational well, losing energy, so that their wavelengths lengthen, an effect called gravitational redshift. The topmost layer may be hydrogen or helium in isolated stars or heavier elements, when accretion has added new material and the resulting spectra record that history. Motion perpendicular to the magnetic field is restricted, which modifies how the gas conducts heat and emits light. Above the atmosphere lies the magnetosphere, a volume filled with charged particles guided by magnetic field lines that loop far from the star. The magnetic field strength is immense, many orders of magnitude stronger than the field at Earth's surface. Electrons and ions spiral around the lines at speeds close to the speed of light, and their motion produces radiation that can be seen across the electromagnetic spectrum. As the star rotates, beams shaped by the magnetic field sweep across space, and an observer on Earth detects a train of pulses. This timing pattern reflects the star's rotation and the geometry of its magnetic poles. Near the magnetic poles, the field funnels particles downward, creating hot spots where energy is deposited into the atmosphere. The Neutron Star Interior Composition Explorer on board the International Space Station measures the resulting X-ray emission and the way it rises and falls as the star spins. From those variations, scientists infer the locations of the hot regions and place limits on the star's radius and mass through models that include light bending and rotation. Rotation inside a magnetic field also induces large electric fields. These fields accelerate particles to energies unattainable in laboratories on Earth. Some particles strike the atmosphere and produce additional high-energy photons, while others escape in a steady outflow called a pulsar wind, carrying energy away and inflating nebulae that shine in X-rays and visible light. In some locations within the magnetosphere, magnetic field lines break and reconnect, converting magnetic energy into heat and particle motion that can trigger brief increases in brightness. The precise locations of acceleration gaps and reconnection regions are not yet fully determined, yet all models agree that the magnetosphere acts as an efficient engine that moves rotational and magnetic energy into radiation and particle winds. Gravity continues to dominate even here. Escape speed at the surface is close to half the speed of light, so thermal motion alone cannot drive gas away. Unless electromagnetic forces accelerate particles outward, matter remains bound, which is why the atmosphere stays so thin. When new matter falls in the magnetosphere, channels it toward the magnetic poles. In accreting systems, this funneled inflow forms columns that strike the surface and heat small areas to extreme temperatures, producing strong X-ray emission. In isolated stars without accretion, surface heating arises mainly from the interior and from return currents of charged particles that complete circuits along magnetic field lines. The outer environment links directly to precise timing measurements. Radio observatories measure pulse arrival times with microsecond accuracy, and small changes in the shape or density of the magnetosphere can shift where and when radiation is emitted and can slightly alter the observed timing. Over long periods, electromagnetic radiation and particle winds extract rotational energy so that the star spins more slowly, a steady increase in the interval between pulses that gives a measure of the torque applied by the fields and the outflow. Short-term irregularities appear as well, and although many of them arise in the crust and the superfluid interior, their signatures are transmitted through the magnetosphere and atmosphere to become visible as changes in the observed pulse sequence. The surface emission also carries information about the star's thermal state. Heat from deeper layers travels outward by conduction through the solid crust and then radiates into space through the atmosphere. Because the magnetic field changes the way electrons move, heat flows more easily along field lines than across them, so the surface temperature varies with magnetic latitude. The resulting pattern of bright and dim areas provides a map of the field near the surface. By comparing observed spectra and pulse shapes with models that include light-bending gravitational redshift and magnetized atmospheres, scientists constrain the star's size and compactness quantities that depend on the internal equation of state, which is the relation among pressure, density, and temperature at extreme conditions. Uncertainties remain in almost every part of this description. Different models of the magnetosphere suggest different altitude ranges for the main emission zones. Some emphasize regions close to the star where fields are strongest, while others favor regions near the light cylinder, where corrotation would otherwise require motion faster than light. Space-based observatories such as the X-ray multi-mirror, Newton satellite, the Chandra X-ray Observatory, and the Fermi Gamma Ray Space Telescope provide complementary information across energies and joint analysis, with the timing precision of large radio arrays continues to refine the physical picture and to remove models that do not fit the observations. In this way, the outer environment of a neutron star serves as the first and most accessible window on conditions that exist at densities and pressures that cannot be produced on Earth. Beneath the magnetosphere and the thin atmosphere lies the outer crust of the neutron star. This layer, although only about 1 kilometer thick, is the first solid boundary where matter exists in a structured lattice rather than as a free plasma. In this region, the pressure of gravity is so intense that atoms cannot hold onto their normal electron clouds. The electrons are stripped away completely, leaving bare nuclei packed into a rigid crystalline lattice that resembles a grid of heavy ions suspended in a sea of free electrons. These electrons are degenerate, which means that they fill all available low-energy states up to a maximum level called the Fermi energy. The degeneracy pressure of these electrons, a quantum mechanical effect, resists further compression and balances some of the weight pressing down from above. At densities around 10 to the power of 9 kilograms per cubic meter, iron-like nuclei dominate the composition because they are stable products of earlier stellar burning. As depth increases, nuclei become progressively more neutron-rich. This happens because the rising pressure squeezes protons and electrons together through a process known as inverse beta decay, producing additional neutrons inside the nuclei. The crust therefore changes composition with depth, each layer characterized by a different set of nuclei in equilibrium with the pressure. The transitions between one nuclear species and another are sometimes sharp forming interfaces where the lattice reorganizes. The lattice is believed to be highly ordered, resembling a body-centered cubic structure at many depths. Such an arrangement minimizes energy under the intense conditions. The rigidity of this lattice makes the outer crust function like the solid surface of the star. It can sustain shear stress, which means it can bend and crack. When stress exceeds the breaking point, sudden shifts occur that release energy into the magnetosphere as star quakes. These events have been linked to changes in pulse timing and to bursts observed in magnetars. Even though the outer crust is thin compared with the star's overall radius, its mechanical properties influence observable behavior on large scales. Electrons in the crust provide electrical conductivity much higher than metals on Earth. This conductivity allows currents to persist for millions of years. The magnetic field threads through the crust and can evolve only slowly because of the high conductivity. When local stresses redistribute currents, the magnetic field changes shape, and energy may be transferred to the magnetosphere. Heat conduction is also dominated by electrons. The crust acts as a pathway that carries thermal energy from deeper regions to the surface where it escapes as X-rays. Cooling observations of young neutron stars depend directly on the ability of the crust to transport heat. As pressure increases with depth, nuclei approach the limits of stability. At around 4 × 10 to the power of 11 kilograms per cubic meter, neutrons begin to drip out of nuclei, marking the transition to the inner crust. Just above this boundary, nuclei are extremely neutron-rich and nearly unstable. The balance between nuclear forces and degeneracy pressure maintains their existence, but the next step downward releases free neutrons. This neutron drip line defines the lower end of the outer crust. In this way, the outer crust bridges ordinary nuclear matter and the exotic states deeper inside. Observationally, the outer crust is not directly visible, but its properties leave signatures. The pattern of glitches, sudden spin-ups observed in pulsar timing reflects the rigidity and breaking strength of the crust. Thermal relaxation after an accretion outburst also provides information because the way the crust cools over years reveals its thermal conductivity and heat capacity. Measurements of these cooling curves have shown that the crust must be relatively transparent to heat, otherwise the surface would not return to equilibrium on the observed timescale. These indirect observations are essential, since direct probing of matter at these densities is impossible in laboratories. Laboratory experiments on Earth help in complementary ways. High-energy collisions in particle accelerators and nuclear physics experiments with neutron-rich isotopes provide data on nuclear masses and decay pathways. These results constrain the models of nuclei expected in the outer crust. While the densities inside a neutron star cannot be reached, the theoretical framework of nuclear physics, combined with astronomical observations, creates a consistent picture. Uncertainties remain especially in the precise equation of state at these densities, but the overall structure of a crystalline lattice of neutron-rich nuclei immersed in a degenerate electron sea is robust. Another important factor is elasticity. The crust can sustain strain up to a breaking threshold that is much higher than materials on Earth. Computer simulations suggest that the breaking strain may be about 1/10 of the total binding force, making the crust the strongest material known in the universe. This extreme strength allows the star to support so-called mountains only a few centimeters high, yet these tiny irregularities can emit continuous gravitational waves as the star rotates. Searches for such waves with detectors like LIGO and Virgo place limits on how asymmetric the crust can be. The outer crust therefore stands as a remarkable combination of solidity and extreme physics, It is rigid enough to fracture and transmit stress, yet permeated by a sea of electrons that carry currents and heat efficiently. Its composition changes with depth as nuclei become more neutron-rich, until the point where neutrons begin to drip free. Although this layer is thin, it forms the platform on which the more exotic inner crust rests, and acts as the immediate gateway between the magnetized atmosphere and the neutron-dominated interior. Every observed glitch, every sudden burst of radiation, and every cooling curve carries information from this crystalline shell. Deeper than the rigid outer crust lies the inner crust, a transitional region, where nuclei and free neutrons coexist. This part of the star extends from the neutron drip boundary down to densities of about half the nuclear saturation density. It is here that the character of matter changes most dramatically, from familiar nuclear forms toward the exotic uniform matter of the core. Unlike the outer crust where nuclei remain intact and form a lattice, the inner crust is a mixture. Nuclei continue to exist, but they are swollen with excess neutrons, and many neutrons are not bound at all. These free neutrons move through the lattice as a gas, and at low temperatures they become a quantum superfluid. The environment is shaped by several competing forces. Gravity presses inward with overwhelming strength, compressing matter to densities far beyond those of atomic nuclei. Degeneracy pressure of neutrons and electrons pushes outward, while nuclear forces hold protons and neutrons together within nuclei. The balance among these effects produces structures that are neither fully nuclear nor fully uniform. The result is a heterogeneous medium of crystalline nuclei, free neutrons, degenerate electrons, and in some layers exotic arrangements known as nuclear paster. The free neutrons in the inner crust have unusual properties. Because they are not charged, they move without feeling the Coulomb repulsion that confines protons. At low temperatures, their wave functions overlap, and they condense into a superfluid. In a superfluid, particles flow without viscosity, meaning no internal friction, resists motion. This property changes the way angular momentum is stored and transferred inside the star. Neutron superfluidity in the inner crust is considered central to the phenomenon of pulsar glitches. In these events, pinned superfluid vortices suddenly unpin and transfer angular momentum to the crust, causing a measurable increase in the rotation rate. The presence of the superfluid is therefore not just a theoretical expectation, but a requirement to explain observational data. The nuclei themselves become progressively distorted as density increases. Close to the bottom of the inner crust, they begin to merge and form extended shapes under the influence of strong nuclear interactions. Instead of spherical nuclei, the matter organizes into rod slabs and other complex geometries collectively called nuclear pasta. These phases minimize energy by balancing the short-range attraction of nuclear forces against the long-range repulsion of protons. The exact arrangements depend on density and proton fraction. Such structures may influence the mechanical strength of the crust, its electrical conductivity, and its ability to support magnetic stresses. Electrons permeate this environment as a nearly uniform background. They provide charge neutrality and contribute to pressure, but they also scatter from the nuclear lattice. Their scattering determines the electrical and thermal conductivity. High conductivity means that magnetic fields decay, slowly preserving the long-term field structure of the star. However, in regions with complex pasta phases, scattering may be enhanced, leading to localized heating or faster magnetic evolution. This interplay between microphysics and large-scale magnetism connects the inner crust to observable activity in magnetars and ordinary pulsars. Heat transport in the inner crust is critical for the thermal evolution of the neutron star. After formation in a supernova, the star cools rapidly by neutrino emission. The crust insulates the core, but over timescales of decades to centuries, heat must flow outward. The rate depends on how easily electrons move through the lattice and scatter from impurities. Observations of cooling in young neutron stars and in accreting systems after outbursts constrain these properties. If the crust were too opaque, the surface would cool more slowly than observed. The agreement between models and data provides strong evidence for high conductivity, consistent with a relatively pure and ordered lattice, even under extreme conditions. Mechanical properties of the inner crust also attract attention. Because of the superfluid neutrons and the elasticity of the lattice, this region can store stress in both forms. The lattice can crack under strain while the superfluid can pin vortices and then release them suddenly. Together they create a system capable of producing irregularities in spin. The amplitude and frequency of observed glitches suggest that the inner crust contains enough superfluid to hold a significant fraction of the star's angular momentum. Current models debate whether the crust alone provides sufficient capacity or whether the outer core also participates. This uncertainty remains one of the open questions of neutron star physics. The inner crust may also play a role in gravitational wave emission. If the lattice of nuclear pasta supports asymmetric stresses, the star could develop tiny deformations. As the star rotates, these deformations radiate gravitational waves. Detectors such as LIGO and Virgo search for such signals, and although none have been confirmed yet, the absence of detection constrains the size of possible deformations, and therefore the breaking strain of the crust. These limits help narrow theoretical models of how nuclear pasta behaves at high density. Another important process in the inner crust is neutrino emission. At certain densities and temperatures, free neutrons scatter and emit neutrinos carrying energy away. These neutrino processes compete with photon emission from the surface in controlling cooling rates. Because neutrinos interact weakly, they escape easily, making them the dominant channel of energy loss in young neutron stars. The presence of superfluidity alters these rates. When pairs of neutrons form and break, neutrinos are produced in bursts, enhancing cooling. Thus, the detailed state of the inner crust, whether normal or superfluid, strongly affects thermal evolution. Experimental input to these questions comes from nuclear physics. Collisions of heavy ions in laboratories can create neutron-rich matter for brief moments, allowing study of how nuclei behave far from stability. Observations of isotopes near the neutron drip line inform models used to describe the inner crust. While laboratory conditions cannot match neutron star densities, they provide crucial benchmarks for theory. By combining such data with astrophysical observations, scientists gradually refine the description of matter in this region. In practical terms, the inner crust acts as a bridge between the relatively familiar solid lattice of the outer crust and the uniform nuclear matter of the core. It is neither entirely solid nor entirely fluid. It contains rigidity, superfluidity, and complex nuclear structures all at once. Each of these properties leaves signatures in observable phenomena: glitches, bursts, cooling curves, and possibly gravitational waves. To understand any of these signals requires careful modeling of the physics at densities where nuclei dissolve and neutrons flow freely. The study of the inner crust continues to highlight how a region only about 1 kilometer thick can control so much of what astronomers see from thousands of light years away. Its mixture of ordered lattice, free neutron sea, and exotic pasta phases makes it one of the most unusual states of matter known. Step by step through theory, experiment, and observation, the description grows more precise, though many uncertainties remain. This transitional shell stands as a critical part of the interior setting, the conditions for the even denser outer core that lies below. At the lower depths of the inner crust, matter begins to take on shapes unlike anything found elsewhere in nature. The extreme balance of forces drives nuclei to deform from ordinary spherical forms into extended configurations. These exotic structures are collectively called nuclear pasta because their geometries resemble familiar shapes such as sheets, rods, or tubes, though the resemblance is only superficial and is used simply as shorthand. They're not macroscopic objects, but arrangements of nucleons organized by the competition between nuclear attraction at short distances and Coulomb repulsion among protons at longer distances. The sequence of structures is predicted to follow density. As compression increases, spherical nuclei begin to merge and form elongated rods, a phase sometimes described as spaghetti. At greater density, these rods connect side by side into wide slabs known as lasagna. Beyond this, the system may invert with voids forming in otherwise uniform matter, creating cylindrical tubes or bubbles, sometimes called gnocchi, or Swiss cheese phases. Each geometry reduces the total energy by optimizing how nucleons are distributed under the combined influences of strong and electromagnetic forces. The transition between phases is gradual with mixed regions and disordered arrangements, rather than sharp boundaries. Although these names are playful, the physics is serious. Nuclear pasta phases change the mechanical and thermal properties of the crust. Their extended structures scatter electrons differently than a regular lattice, reducing electrical and thermal conductivity. This influences how magnetic fields evolve over time and how heat flows from the core to the surface. In magnetars, rapid changes in field configuration may depend on whether the crustal pasta can redistribute currents. Similarly, observations of cooling after accretion outbursts provide indirect evidence of how conductive the pasta layers are. The geometry also affects mechanical strength. Computer simulations suggest that pasta phases may form one of the strongest known materials. Their connected networks can withstand greater strain than simple crystal lattices. This strength could allow the star to support slightly larger deformations than the outer crust, alone potentially increasing the amplitude of gravitational waves emitted as the star rotates. Continuous gravitational wave searches aim to detect such signals, and upper limits already constrain the maximum strain nuclear pasta can endure. Another important effect is on neutrino interactions. The complex geometry changes how neutrinos scatter, possibly trapping them longer, or letting them escape more easily depending on the density and arrangement. This modifies the cooling curve of the star. Because young neutron stars lose energy mainly by neutrino emission, even small differences in scattering rates can change the thermal history. Detailed models attempt to include the influence of pasta, but uncertainties remain large, and future observations of cooling neutron stars may provide tests. Nuclear pasta is not directly observable, but indirect clues accumulate. Timing irregularities called glitches require strong pinning of superfluid vortices. Pasta phases may provide the pinning sites anchoring vortices until stresses exceed thresholds and sudden releases occur. In this way, the microphysics of nucleon arrangements could explain macroscopic jumps in rotational frequency measured across thousands of light years. The persistence and distribution of such glitches suggests that pinning is widespread, consistent with extensive pasta layers. Simulations use molecular dynamics techniques to model billions of nucleons interacting under strong and Coulomb forces. These models reveal spontaneous emergence of rod slabs and other shapes when density reaches appropriate ranges. While such calculations cannot replicate every detail of real neutron star matter, they give confidence that the basic picture is correct. Variations in symmetry, defects, and disorder are expected much like in solids on Earth, but overall the extended shapes remain stable at neutron star conditions. experiments on Earth cannot create nuclear pasta directly, but heavy ion collisions give hints about how nuclear matter behaves when pushed toward extreme neutron richness and density. Observations of isotopes far from stability show how nuclear forces operate under imbalanced conditions. By extrapolating from these data, theorists constrain models that predict pasta formation. The agreement between independent methods strengthens the case that pasta is an inevitable feature of neutron star interiors. The presence of pasta also influences magnetic reconnection events. In regions where conductivity is reduced, magnetic stress may build up unevenly, leading to sudden rearrangements. Magnetar flares, some of the brightest events in the galaxy, may be triggered by such crustal instabilities. Although many details remain uncertain, the idea that the microstructure of matter shapes astrophysical phenomena is one of the remarkable outcomes of neutron star physics. Heat capacity in the pasta region is also noteworthy. Because the structures involve many nucleons linked together, they can store thermal energy differently than isolated nuclei or uniform matter. This modifies the rate at which the crust cools and relaxes after heating. Observations of transient systems where accreted material suddenly halts and the crust cools back to equilibrium show timescales that agree with models including pasta. These comparisons provide rare observational leverage on a region otherwise beyond reach. Even though nuclear pasta layers are narrow compared with the whole star, they represent one of the most exotic states of matter known. The combination of nuclear and Coulomb forces sculpting matter into rods and slabs is unique to the environment, where density is just below nuclear saturation. Neither lower density solids nor higher density uniform nuclear fluids support such arrangements. This intermediate regime therefore reveals the versatility of fundamental forces under conditions inaccessible elsewhere. Theoretical uncertainty remains regarding the exact density ranges, thickness, and influence of defects. Some models predict smooth transitions while others allow for abrupt phase changes. The geometry may vary depending on temperature, magnetic field strength, and composition. These uncertainties leave room for observational tests. Future instruments capable of measuring neutron star cooling with higher precision or gravitational wave detectors with greater sensitivity may provide answers. Step by step, the description of pasta phases connects microscopic nucleon behavior to macroscopic astrophysical signatures. It shows how the balance of forces at the scale of femtometers influences radiation timing and cooling observed across light years. This connection underscores the unity of physics from the smallest to the largest scales without requiring metaphors or exaggeration. Nuclear pasta remains one of the clearest examples of matter adopting entirely new states under conditions far from ordinary experience, and it marks the final boundary before the onset of the uniform fluid of the outer core. Beneath the layers of the inner crust and the nuclear pasta lies the outer core of the neutron star. This region contains the majority of the star's mass and volume. Its density rises from about 1/2 of nuclear saturation density at the top to 2 or 3 times nuclear saturation density deeper within. Matter here is no longer organized into discrete nuclei. Instead, it exists as a uniform fluid composed mostly of neutrons with a smaller fraction of protons, electrons, and in some cases muons. The outer core is the place where the extreme balance of forces between quantum degeneracy nuclear interactions and gravity reaches a relatively stable form. The outer core is dominated by neutrons, but a small fraction of protons is required to maintain charge neutrality with the surrounding electrons. Electrons exist as a highly degenerate gas-filling available energy states up to very high energies. At sufficient densities, electrons can gain energy large enough to convert into muons, heavier relatives of electrons through weak interactions. Muons then share the task of balancing the positive charge of protons. This mixture of neutrons, protons, electrons, and muons is often referred to as NPEM matter. One of the defining features of the outer core is superfluidity of neutrons and superconductivity of protons. When density and conditions are right, neutrons form pairs similar to Cooper pairs in conventional superconductors, and these pairs condense into a superfluid state. This superfluid flows without resistance and supports the formation of quantized vortices that store angular momentum. Protons, though, a minority, can also pair through attractive channels and enter a superconducting phase. Because protons are charged, their superconductivity interacts directly with magnetic fields. The fields thread the superconductor in quantized flux tubes, and the arrangement of these tubes may interact with the vortices of the neutron superfluid. The interplay between vortex lines and flux tubes provides a possible explanation for sudden changes in rotation, rate magnetic evolution, and other dynamic events observed in neutron stars. Pressure in the outer core arises mainly from the degeneracy of neutrons and the repulsion of nuclear forces at short range. Quantum mechanics prevents neutrons from occupying the same state, so as density rises, they are forced into higher momentum states, creating a strong outward pressure. Nuclear interactions add further complexity. At densities below nuclear saturation, attraction dominates binding nucleons together. At and above saturation, repulsion grows stronger, stiffening the equation of state. The balance of these effects determines how compressible the outer core is, and therefore sets the relationship between mass and radius of the entire star. Measurements of neutron star radii from X-ray observations and constraints from gravitational wave signals during mergers feed directly into models of the outer core. The thermal behavior of the outer core is also important. Newly born neutron stars are extremely hot with temperatures exceeding billions of degrees, but they cool quickly. The primary channel of energy loss is neutrino emission. In the outer core, one of the dominant processes is the modified Urca process, where a neutron converts to a proton while emitting an electron and an antineutrino with a bystander nucleon assisting to conserve momentum. The inverse process also occurs, although slower than direct Urca reactions which require higher proton fractions. The modified Urca process is efficient enough to drive cooling over thousands of years. When conditions allow, the direct Urca process cooling accelerates dramatically. Whether a given star can undergo direct Urca reactions depends on the composition and equation of state, so observations of cooling rates provide constraints on core physics. Another source of neutrinos comes from the pairing of nucleons. When neutron or proton pairs form and break in the superfluid or superconducting states, neutrinos are emitted. This pair breaking and formation process can temporarily enhance cooling and leave observable imprints on thermal evolution. For example, the observed rapid cooling of the neutron star in the Cassiopeia, a supernova remnant, has been interpreted as evidence for the onset of neutron superfluidity in its core. This represents one of the strongest pieces of indirect evidence that the outer core contains superfluid neutrons. Magnetic fields penetrate the outer core through quantized flux tubes in the proton superconductor. The arrangement and motion of these flux tubes influence how the magnetic field evolves over thousands to millions of years. Interactions with neutron vortices may either pin the structures or allow relative motion depending on conditions. If vortices and flux tubes pin, strongly stress builds until sudden unpinning occurs, possibly linked to glitches or magnetar flares. If they move more freely, the star's magnetic field may decay more smoothly. These microphysical processes thus connect to observable large-scale magnetic behavior. The outer core also controls the moment of inertia of the neutron star. Because it contains most of the mass, its response to changes in rotation, internal stresses or external torque sets the overall dynamics. For example, when the crust experiences a quake or a rearrangement of magnetic stress, the reaction of the outer core determines whether the star's spin adjusts smoothly or abruptly. Models that include both crust and core superfluids attempt to reproduce the wide variety of observed pulsar glitch behavior. Laboratory nuclear physics contributes valuable information here. Experiments on heavy ion collisions probe the equation of state of dense matter up to and slightly beyond nuclear saturation. Measurements of neutron skin thickness in heavy nuclei, such as lead, provide clues about how pressure builds with neutron excess. These data inform models used to extrapolate into the conditions of the outer core. Although no experiment can reach the densities directly, the combination of laboratory results and astrophysical observations narrows possibilities. Gravitational wave astronomy has added a new channel of information. During neutron-star mergers, the tidal deformability of each star influences the gravitational wave signal. Tidal deformability depends on the equation of state of the outer core. When the binary neutron-star merger G-817 was detected in 2017, analysis of the signal provided constraints on how stiff or soft the outer core could be. The results favored intermediate stiffness, ruling out extremes. This demonstrates how observations across cosmic distances feed back into the microscopic description of matter. The outer core is therefore the backbone of the neutron star. It holds most of the mass sets, the radius regulates cooling, and stores angular momentum. Its properties emerge from fundamental nuclear and particle interactions under densities unreachable by terrestrial experiment. While uncertainties remain particularly about the exact equation of state and the degree of superfluidity and superconductivity, the outer core stands as the best understood large region of the star. It bridges the structured crust above with the even denser and less certain inner core below, forming the stable environment in which many of the star's observable behaviors originate. The neutron superfluid within the star plays a central role in the dynamics of its rotation and the transport of energy. A superfluid is a state of matter in which particles move collectively without viscosity. In the environment of the neutron star, the density is so high and the temperature so low that neutrons pair up through attractive channels of the nuclear force. These pairs condense into a coherent quantum state, allowing bulk motion without resistance. This property is not a speculation drawn from analogy, but a robust prediction of nuclear physics extended to extreme densities supported by several indirect astronomical observations. The onset of superfluidity changes the way angular momentum is stored. In an ordinary rotating fluid, circulation can vary continuously, but in a superfluid, rotation is quantized. The rotation is supported by an array of vortices, each carrying a fixed quantum of circulation. The number of vortices is proportional to the angular velocity of the superfluid. As the neutron star spins down over time due to electromagnetic radiation and particle winds from the magnetosphere, the superfluid vortices must gradually move outward and be expelled to reduce the overall rotation rate. If vortices are pinned to the nuclear lattice of the inner crust or to flux tubes in the superconducting proton fluid, they can become stuck, preventing smooth adjustment. Stress builds until many vortices suddenly unpin and move outward, transferring angular momentum to the crust. This produces a measurable spin-up called a glitch. The recovery after a glitch reflects the gradual re-establishment of equilibrium between the crust and the superfluid interior. The presence of a neutron superfluid also affects thermal properties. When pairs of neutrons form and break, they emit neutrinos. This pair breaking and formation process provides an efficient cooling channel, particularly at the temperatures of young neutron stars. Observed rapid cooling in specific stars such as the neutron star in Cassiopeia has been interpreted as evidence for the onset of superfluidity in its core. Theoretical models without superfluidity cannot explain the speed of the observed temperature decline. Thus, thermal evolution provides strong indirect confirmation of the existence of neutron superfluid phases. Superfluidity also changes the response of the star to oscillations. Modes of vibration such as R-mode oscillations driven by rotation and gravitational wave emission interact differently when superfluid components are present. Mutual friction between the superfluid vortices and the normal components of matter damps certain oscillations. This damping is important because it can stabilize or destabilize modes that might otherwise grow by emitting gravitational waves. The balance between gravitational wave driving and superfluid damping influences whether neutron stars can be sources of continuous gravitational waves detectable by instruments on Earth. In addition to vortices, the geometry of the superfluid is influenced by the interaction with the superconducting proton component. If vortices intersect magnetic flux tubes, the pinning and unpinning dynamics become even more complex. Some models propose that the motion of vortices through a dense forest of flux tubes explains not only glitches, but also timing noise, the small irregular variations in spin frequency seen in many pulsars. The detailed microphysics of vortex flux tube interactions remains uncertain, but it is one of the major topics of theoretical and computational work in neutron star physics. The neutron superfluid is not a uniform sea throughout the star. Different regions may support different pairing states depending on density and the balance of nuclear forces. In the inner crust, neutrons are expected to pair in a singlet state forming what is called S-wave superfluidity. In the outer core, neutrons likely pair in a triplet state known as P-wave or P2 superfluidity, where the angular momentum of the pair is not zero. These differences change the critical temperature at which superfluidity forms and the energy gap that influences neutrino emission rates. Observational signatures of cooling and glitch behavior are used to infer which type of pairing occurs where. Another consequence of superfluidity is its effect on heat transport. Because superfluids can carry entropy differently than normal fluids, they change how temperature gradients evolve inside the star. Superfluid phonons, the quantum excitations of the superfluid, contribute to thermal conductivity. This influences how heat deposited in one region, perhaps by accretion or magnetic reconnection, spreads through the interior. Cooling curves of accreting neutron stars during quiescence depend on these transport processes, and fits to the data provide constraints on the properties of the superfluid. Laboratory evidence for neutron superfluidity is indirect but strong. In heavy nuclei, neutron pairing is observed and influences binding energies and excitation spectra. In ultra-cold atomic systems, experiments with fermionic atoms cooled to near absolute zero demonstrate superfluid pairing similar in principle to what occurs among neutrons. Although densities are vastly different, these systems show that fermion pairing and condensation into superfluid states is a general physical phenomenon. By combining such laboratory knowledge with nuclear theory and astrophysical data, scientists build confidence in the reality of neutron superfluidity in stars. The role of the neutron superfluid extends beyond internal physics. It determines how stable pulsar rotation can be as a cosmic clock. Some pulsars exhibit timing stability comparable to atomic clocks on Earth, while others show irregularities. The difference may stem from how vortices move through the superfluid interior and how strongly they couple to the crust. Long-term monitoring of pulsars reveals patterns of glitches and timing noise that encode the behavior of billions of vortices. By comparing data with theoretical models, researchers attempt to reconstruct the microphysics from macroscopic timing records. The superfluid is therefore both a microscopic quantum system and a macroscopic driver of observable astrophysical phenomena. Its vortices explain sudden spin changes its neutrino emission controls, cooling its interactions with flux tubes influence magnetic evolution, and its transport properties shape thermal relaxation. These diverse roles show how a quantum condensed state formed under conditions of extreme density becomes central to the behavior of an entire star. Even though direct probes are impossible, the convergence of evidence from timing cooling and theoretical physics makes the existence of neutron superfluidity inside neutron stars one of the most secure conclusions in modern astrophysics. Alongside the neutron superfluid, the outer core also hosts proton superconductivity. While neutrons dominate by number, the minority population of protons interacts with magnetic fields because of their charge. Under the extreme density and relatively low temperature of the neutron star interior, protons form Cooper pairs, similar to those in laboratory superconductors. These pairs condense into a superconducting state, where electrical resistance vanishes and magnetic fields penetrate only in quantized bundles called flux tubes. The presence of superconductivity changes how the magnetic field is structured and how it evolves, linking microscopic physics to macroscopic astrophysical observations. In ordinary materials, superconductivity can be of type 1 or type 2. Type 1 superconductors expel magnetic fields entirely, while type 2 superconductors allow fields to penetrate in quantized vortices. Current models indicate that proton superconductivity in neutron star matter is type 2. This means that magnetic fields do not vanish from the core, but instead thread the region through an enormous number of flux tubes. Each tube carries a fixed amount of magnetic flux and has a narrow core where superconductivity is suppressed. These flux tubes interact with the surrounding neutron superfluid vortices, leading to a complex and dynamic interior structure. The density of flux tubes depends on the strength of the magnetic field. For typical neutron stars with fields around 10 to the power of 12 Gauss, the number of flux tubes per square centimeter is immense, reaching values far beyond any terrestrial system. In magnetars, where fields can exceed 10 to the power of 15 Gauss, the density is even greater. The interaction between such a dense forest of flux tubes and the neutron superfluid vortices is thought to be responsible for phenomena like glitches and post-glitch relaxation. If vortices become pinned to flux tubes, angular momentum exchange between the superfluid and the crust may be hindered, and sudden unpinning events can lead to rapid spin adjustments. Proton superconductivity also influences thermal and magnetic evolution. Because electrical resistance vanishes, magnetic fields can remain trapped for long time scales, evolving only through motion of flux tubes or by dissipative processes at their boundaries. The drift and rearrangement of flux tubes may lead to gradual field decay, while collective movements triggered by stress could produce sudden magnetic activity. This is relevant to magnetar bursts, where large amounts of magnetic energy are released in a short time. The details of flux tube mobility, pinning strength, and interaction with neutrons are active areas of research. Another major consequence of proton superconductivity is its effect on neutrino emission. Similar to neutrons, when proton pairs form and break, neutrinos are produced. This pair breaking and formation process contributes significantly to cooling. The onset of proton superconductivity therefore leaves an observable imprint on thermal evolution. In some models, the rapid cooling observed in the Cassiopeia, a neutron star, requires both neutron superfluidity and proton superconductivity, with their combined effects producing the observed decline in surface temperature. This dual condensation of neutrons and protons into quantum states highlights the unique character of neutron star interiors. The behavior of flux tubes within the proton superconductor is central to understanding magnetic field evolution. Flux tubes can pin to the crust at the boundary anchoring magnetic fields. If the star's rotation changes, neutron vortices try to move relative to the flux tubes. Interactions between the two can transfer momentum or cause local rearrangements. Some theoretical models suggest that large-scale motion of flux tubes driven by spin down and coupled to vortex motion could be responsible for magnetic field decay over millions of years. Observationally, pulsars with lower fields and older ages do show gradual field weakening consistent with such processes. Superconductivity also alters the specific heat of the core. When protons form pairs, the number of available excitations decreases, reducing the ability of the matter to store thermal energy. This lowers the specific heat and changes the timescale of cooling. Neutrino emissivity is also suppressed once pairs are fully formed, except during the initial pair formation phase when emission is enhanced. Thus, the presence of superconductivity changes the cooling history in subtle but detectable ways. Long-term monitoring of isolated neutron stars provides data to test these theoretical predictions. Proton superconductivity is not uniform across the core. Its strength and character depend on density. Models predict that near the crust core boundary, where density is lower, proton pairing is strong, while deeper in the core pairing weakens or disappears. This spatial variation influences how magnetic fields are distributed and whether they can move freely in certain layers. The spatial map of superconductivity therefore matters for global magnetic field evolution. Theoretical studies using microscopic nuclear interactions attempt to calculate these variations, but uncertainties remain, and astrophysical data are essential to constrain them. Evidence for proton superconductivity comes indirectly through its combined role with neutron superfluidity in explaining observed cooling and glitches. No laboratory experiment can create matter at these densities, but theoretical understanding of nuclear pairing along with the success of models that include both condensates makes the case compelling. The precise critical temperature at which proton pairs form is uncertain, but estimates range from about 10 to the power of 9 to 10 to the power of 10 Kelvin. Since neutron stars cool rapidly after birth, their cores likely enter the superconducting state within years or decades, remaining so for most of their lifetimes. Proton superconductivity also raises interesting possibilities for gravitational wave emission. If flux tubes pin unevenly and support asymmetric stresses, the star may develop tiny irregularities. These irregularities can radiate continuous gravitational waves as the star rotates. Searches for such signals provide upper limits on deformation, and therefore constrain models of flux tube pinning strength. Although no detection has yet been made, future improvements in sensitivity may probe these subtle effects. The combination of neutron superfluidity and proton superconductivity makes the neutron star outer core one of the most complex condensed matter systems in the universe. Two different quantum fluids coexist, one neutral and one charged, interacting with each other through vortices and flux tubes. Their collective behavior determines the spin magnetism and cooling of the star, connecting microscopic quantum physics to macroscopic astrophysical signatures. This coexistence is not an incidental feature but an essential element of the neutron star's stability and observable behavior. Beneath the outer core lies a region that is less certain the possible inner core. The physics here pushes beyond densities that can be constrained directly by experiments or well-tested nuclear theory. At these depths, the density may rise to several times nuclear saturation conditions under which new degrees of freedom might appear. The outer core is understood as a mixture of neutrons, protons, electrons, and muons, but the inner core could contain particles not present elsewhere, such as hyperons, meson condensates, or even deconfined quark matter. The uncertainty reflects the limits of current knowledge, and the description of the inner core remains one of the most active frontiers of neutron star research. One possibility is the presence of hyperons particles that contain strange quarks in addition to up and down quarks. Examples include the lambda sigma and Xi baryons. At densities beyond 2 or 3 times nuclear saturation, it becomes energetically favorable for neutrons to convert into hyperons through weak interactions, reducing the overall Fermi energy. If hyperons appear, they soften the equation of state, meaning the pressure for a given density is lower. This can reduce the maximum mass a neutron star can support. Observations of neutron stars with masses around 2 times that of the Sun challenge models with abundant hyperons, because too many hyperons would prevent the star from reaching such high masses. This discrepancy is known as the hyperon puzzle. Proposed solutions include strong repulsive interactions among hyperons or modifications of nuclear forces that stiffen the equation of state at high density. Another possible state is a meson condensate. Pions or kaons, which are mesons composed of quark-antiquark pairs, may condense into macroscopic quantum states at high density. If kaon condensation occurs, negative kaons can replace electrons in balancing charge, leading to new cooling channels through enhanced neutrino emission. Such rapid cooling has not been widely observed, which constrains how likely meson condensates are in real stars. Theoretical studies continue to examine the conditions under which condensation might appear, but clear observational evidence is lacking. The most dramatic possibility is deconfined quark matter. At sufficiently high density, nucleons may dissolve into their constituent quarks, producing a uniform fluid of up-down and possibly strange quarks. This state is sometimes called strange quark matter. If realized, it could exist as a core within neutron stars, or in the extreme case form entire self-bound strange stars. The presence of quark matter would alter the equation of state, and might explain certain astrophysical signatures such as small radii or unusual cooling rates. Gravitational wave signals from neutron star mergers provide new constraints, since the tidal deformability of the stars depends on whether quark matter cores are present. The debate remains open with no consensus yet. Some models propose hybrid stars with an outer region of nucleonic matter and an inner core of quark matter separated by a sharp first-order phase transition. In such models, the star may have a distinctive mass-radius relation, sometimes producing twin stars, 2 different radii for the same mass depending on whether the core has transitioned. Observations of neutron stars through X-ray timing and gravitational waves may be able to detect or exclude such features. Future data with higher precision will be essential for resolving this question. The inner core also raises questions about superfluidity and superconductivity at higher densities. If hyperons or quarks exist, they too may form paired states. Hyperons might form superfluids, and quarks could form color superconducting phases where quarks pair in ways that involve color charge. These exotic condensates would alter cooling neutrino emission and transport properties. Theoretical studies of color superconductivity predict energy gaps and critical temperatures, but connecting these to observational evidence is extremely challenging. Another layer of uncertainty comes from the possibility of phase transitions that are not sharp but continuous crossovers. In that case, matter evolves smoothly from nucleonic to quark-dominated without a clear boundary. Such transitions are harder to detect observationally, but they may influence the stiffness of the equation of state and therefore the mass-radius curve. The nature of the transition, whether first order or crossover, remains a subject of ongoing research in quantum chromodynamics. Despite these uncertainties, constraints exist. Observations of massive neutron stars close to 2 solar masses show that the equation of state cannot be too soft, otherwise the stars would collapse into black holes. Measurements of radii from NICER suggest values around 11 to 13 kilometers for stars of about 1.5 solar masses. Gravitational wave observations from mergers add tidal deformability limits. All these constraints reduce the range of possible models. While they do not uniquely determine whether hyperons, condensates, or quark matter exist, they force any proposed theory to remain consistent with data. Cooling observations also provide clues. If rapid cooling channels such as direct Urca processes with hyperons or mesons were common, many neutron stars would appear cooler than observed. The fact that most observed stars follow slower cooling curves suggests that either these channels are suppressed or that only some stars reach the conditions for exotic cores. This selective appearance may depend on mass, with heavier stars crossing thresholds for new phases while lighter stars do not. Such a mass dependence would explain why some neutron stars show unusual behavior while others do not. The inner core remains inaccessible to direct laboratory experiments. Even heavy ion collisions at the most powerful accelerators achieve only a fraction of the densities and probe higher temperatures, rather than the low temperature regime relevant to neutron stars. Lattice quantum chromodynamics calculations, which simulate strong interactions on supercomputers, face difficulties at high density because of the sign problem. Nevertheless, progress continues, and approximate methods combined with astrophysical data may gradually narrow the possibilities. In summary of what is known the inner core of a neutron star could contain: hyperons, meson condensates, or deconfined quark matter. Each possibility carries distinctive consequences for the equation of state cooling and observable properties. Current data do not yet discriminate among these possibilities with certainty. What is clear is that the inner core operates at densities where new physics must emerge beyond what has been confirmed in the outer core. Future observations of neutron star mergers, more precise mass and radius measurements, and better theoretical understanding of strong interactions will be necessary to determine the true composition. For now, the inner core remains the most mysterious part of the neutron star interior, a domain where established physics meets its limits, and where multiple possibilities remain viable. The structure of a neutron star is maintained by a delicate balance between gravity and various forms of pressure. Gravity presses inward with overwhelming force. At the surface, the gravitational acceleration is about 100 billion times stronger than that on Earth, and deeper within it grows even more intense. Left unchecked, this pull would compress matter until it collapsed into a black hole. What prevents this collapse is pressure arising from several sources: electron degeneracy in the outer crust, neutron degeneracy in the core, and the repulsive part of the strong nuclear force when nucleons are packed too tightly. Degeneracy pressure is a direct consequence of quantum mechanics. Fermions, which include electrons, neutrons and protons, cannot occupy the same quantum state. In dense matter, particles are forced into higher momentum states, until all states up to the so-called Fermi surface are filled. This filling produces a pressure even at zero temperature. For electrons in the crust, degeneracy pressure is what prevents the outer layers from collapsing despite gravity. For neutrons in the core, neutron degeneracy pressure provides a much stronger resistance because the densities involved are vastly greater. This pressure scales with density in a way that stiffens the star, maintaining its structure against the inward pull. nuclear forces add another essential contribution. At distances of a few femtometers, nucleons attract each other, which is what holds atomic nuclei together. However, at even shorter distances, the force becomes strongly repulsive. In the core of a neutron star, where nucleons are nearly touching, this repulsion provides additional pressure that stiffens the equation of state. Without it, neutron degeneracy alone would not be sufficient to support the most massive observed stars. Models that reproduce neutron star masses above 2 solar masses rely on this repulsive interaction to provide the necessary support. Magnetic pressure can also play a role, though it is generally secondary compared with degeneracy and nuclear forces. In magnetars, fields can reach 10 to the power of 15 Gauss. At such strength, the energy density of the magnetic field is comparable to that of matter at lower densities in the crust. Magnetic pressure can locally support or distort regions of the crust, influencing star quakes and flares. However, in the global balance of the star, magnetic forces remain much smaller than degeneracy and nuclear pressures. Rotation contributes another form of support. A rapidly rotating neutron star experiences centrifugal forces that oppose gravity most strongly at the equator. This effect slightly flattens the star into an oblate spheroid. For millisecond pulses which rotate hundreds of times per second, the centrifugal support is significant enough to change the maximum mass and radius by a small fraction. Rotation also modifies oscillation modes and the stability of the star. Nevertheless, the fundamental competition is always between gravity, which drives collapse, and the combination of degeneracy and nuclear forces which provide pressure. The equation of state, which describes how pressure depends on density, encapsulates this balance. A stiff equation of state provides high pressure at a given density, leading to larger radii and higher maximum masses. A soft equation of state provides less pressure, leading to smaller stars that cannot reach as high a mass before collapsing. Observations of neutron star mass and radius directly test these models. The detection of stars with masses around 2 solar masses rules out very soft equations of state, while radius measurements from X-ray observations and gravitational wave constraints on tidal deformability rule out some very stiff equations. The surviving models define a band of possibilities, each representing a different balance of the same fundamental forces. At the limit, when mass exceeds what pressure can support, collapse occurs, producing a black hole. The maximum mass a neutron star can support, known as the Tolman-Oppenheimer-Volkoff limit, depends on the equation of state. Current constraints place it around 2.5 to 3 solar masses. This boundary is not known precisely because it depends on the uncertain physics of the inner core. However, the principle is clear: beyond this mass, no combination of degeneracy and nuclear repulsion can prevent collapse. The balance of forces also explains why neutron stars have such small radii relative to their mass. With masses of 1 to 2 solar masses compressed into radii of about 12 kilometers, average densities reach several times nuclear density. This extreme compactness means that relativistic effects are crucial. General relativity modifies the balance by strengthening gravity compared with Newtonian predictions. Solutions to the Tolman-Oppenheimer-Volkoff equations show that relativistic corrections are essential for accurate structure models. In practice, the balance of forces must be computed using relativistic stellar structure equations, not simple Newtonian approximations. One manifestation of the balance is in the surface gravity and escape velocity. Because pressure supports the star just short of collapse, the escape velocity from the surface is about half the speed of light. This leads to strong gravitational redshift of radiation, leaving the surface, and to strong light bending where photons are deflected so much that an observer can see more than half the star at once. These phenomena are observable consequences of the same balance that prevents collapse. The balance is also tested during dynamic events. In a merger of two neutron stars, tidal forces compress and heat the matter. The way the merged object resists collapse for a brief time before forming a black hole depends on the same interplay of pressures. Gravitational wave signals from such mergers carry information about the stiffness of matter and therefore about the balance of forces. In this way, observations of mergers provide direct tests of how strong pressure can be at extreme densities. Laboratory experiments, while unable to reach neutron star densities, probe the forces that contribute to pressure. Measurements of nuclear interactions, scattering experiments and studies of neutron-rich isotopes all inform the parameters used in equations of state. Heavy ion collisions generate compressed nuclear matter for fleeting moments, offering data on how matter responds to pressure. These inputs anchor theoretical models that extend into the far denser regime of neutron stars. The balance between gravity and pressure is not static. As the star cools and spins down, the equilibrium can change subtly. For example, the loss of rotational support leads to a slow contraction, altering the density distribution. Such changes may trigger star quakes in the crust as the solid shell adjusts. Similarly, magnetic field decay can redistribute stresses affecting local balances. Yet the overall structure remains stable over millions of years because the fundamental forces maintain the same global equilibrium. In essence, the existence of neutron stars demonstrates the ability of quantum mechanics and nuclear physics to resist one of nature's most powerful forces, gravity. Without degeneracy pressure and nuclear repulsion, the core of a supernova would collapse directly into a black hole. With them, the collapse halts at a density where pressure and gravity are equal. The neutron star remains suspended at this point of balance, a stable configuration that continues to shine through pulses and bursts. Understanding this equilibrium is central to understanding all other aspects of neutron star behavior, because every observable property emerges from this underlying balance of forces. Rotation is one of the defining properties of a neutron star. When the core of a massive star collapses during a supernova conservation of angular momentum forces, the remnant to spin far faster than the progenitor. A star that once rotated in days can leave behind a neutron star rotating many times per second. The initial spin period depends on the mass distribution of the collapsing star, the efficiency of angular momentum transfer, and interactions during the explosion. Newly formed neutron stars can rotate at hundreds of revolutions per second, and even as they age, their rapid spin remains a central part of their identity. The spin shapes the observable signals. If the magnetic axis of the neutron star is not aligned with the rotational axis, the magnetic field channels radiation into beams that sweep across space like a lighthouse. An observer who lies in the path of the beams detects pulses of radio waves, X-rays or gamma rays at the exact frequency of the star's rotation. These regular pulses give rise to the term pulsar. The stability of the rotation is remarkable. Some pulsars maintain timing precision comparable to the best atomic clocks on Earth, allowing astronomers to use them as tools to detect gravitational waves and to study interstellar space. Rotation also modifies the star's structure. Centrifugal forces act outward most strongly at the equator, making the star ablate. For the fastest spinning millisecond pulsars, the equatorial radius is several percent larger than the polar radius. This flattening influences how the interior supports pressure and slightly changes the maximum mass the star can sustain before collapsing into a black hole. The interplay between rotation and the equation of state is studied through models of rotating relativistic stars. These models predict maximum spin rates beyond which the star would shed mass. The fastest known pulsar rotates about 700 times per second, close to the theoretical breakup limit. The spin rate does not remain constant. Over time, neutron stars lose angular momentum. The main mechanisms are electromagnetic radiation from the magnetosphere particle winds and possibly gravitational wave emission if the star has asymmetries. The result is a gradual increase in the observed pulse period, a process known as spin down. The rate of spin down depends on the strength of the magnetic field and the alignment between the rotation and magnetic axes. Measurements of spin down allow astronomers to estimate the age of pulsars and to infer their magnetic field strength. Glitches interrupt this smooth spin down. These are sudden increases in rotation rate observed as small but measurable jumps in the pulse frequency. Glitches are believed to result from interactions between the crust and the superfluid interior. When superfluid vortices pinned in the crust suddenly unpin and move outward, angular momentum is transferred to the crust, spinning it up. The frequency of glitches varies among pulsars. Some show many glitches each year while others remain stable for decades. The study of glitches provides insight into the microphysics of superfluids and crustal structure. Timing noise is another irregularity. Unlike glitches, which are abrupt timing, noise appears as slow wandering of the spin frequency. The causes are less clear but may involve variations in the magnetosphere, torque fluctuations, or complex interactions between the crust and the interior. While less dramatic than glitches, timing noise complicates efforts to use pulsars as precise clocks. Understanding it requires linking magnetospheric processes with interior physics, a challenge that continues to drive research. Rotation also interacts with oscillation modes. Certain modes, called R modes, are driven unstable by gravitational wave emission in rapidly rotating stars. If damping mechanisms such as superfluid mutual friction are insufficient, R modes could grow and carry away angular momentum, limiting spin rates. The absence of very fast pulsars beyond the observed maximum may reflect this instability. Searches for continuous gravitational waves from young, rapidly rotating neutron stars aim to detect or constrain R-mode activity. Accretion in binary systems changes rotation dramatically. When a neutron star pulls matter from a companion star, the infalling gas transfers angular momentum. Over millions of years, this process can spin up the neutron star to millisecond periods. These spun-up pulsars, called recycled pulsars, often have weaker magnetic fields and extraordinary timing stability. Their existence confirms theoretical expectations about angular momentum transfer and provides natural laboratories for testing gravitational physics. Some recycled pulsars are found in binaries with white dwarfs, where their precise timing has been used to confirm aspects of general relativity such as orbital decay due to gravitational wave emission. The relationship between rotation and magnetism is also important. Magnetic dipole radiation is the main driver of spin down. If the magnetic field decays over time, the torque decreases and the spin down slows. Observations suggest that field decay is faster in young, strongly magnetized magnetars and slower in older pulsars. This interplay shapes the evolutionary tracks of neutron stars in the period-period derivative diagram, a tool that maps their lifetimes and transitions between classes. Another consequence of rotation is the potential to emit gravitational waves if the star is not perfectly symmetric. Even tiny mountains, only a few centimeters high, supported by the strength of the crust, could produce detectable signals if the star rotates fast enough. Searches with gravitational wave detectors such as LIGO and Virgo place limits on such deformations. Although no continuous signals have been found, yet the upper limits already constrain the breaking strain of neutron star crusts and the possible asymmetry supported by magnetic or elastic stresses. Rotation also affects thermal evolution. As the star spins down, its interior adjusts, leading to gradual compression. This can trigger reactions such as pycnonuclear fusion in the crust, where nuclei fuse under high pressure, releasing heat. This deep crustal heating contributes to the thermal balance, particularly in accreting stars where spin down and compression proceed continually. Thus, rotation is not only a kinematic property, but also a driver of nuclear processes deep inside the star. The study of rotation provides a link between fundamental physics and astrophysical observation. By measuring spin periods, their derivatives, glitches, and timing noise, astronomers infer conditions inside the star that cannot be probed directly. Each rotation-related phenomenon encodes information about superfluid vortices, magnetic fields, crustal strength, and possible gravitational wave emission. In this way, rotation serves as a window into the star's interior, allowing the physics of dense matter to be studied through precise timing of pulses across cosmic distances. Among the most striking behaviors of neutron stars are glitches and star quakes, sudden changes in rotation, or bursts of activity that reveal the coupling between the crust and the superfluid interior. A glitch is observed as a rapid spin-up of the star, a small but measurable increase in the pulse frequency. These events contrast with the otherwise steady spin-down caused by electromagnetic braking. Glitches provide one of the most direct windows into the dynamics of superfluid vortices and crustal stresses. The prevailing model links glitches to the motion of superfluid vortices. Inside the crust, neutrons exist in a superfluid state. Rotation in this superfluid is carried by an array of quantized vortices. Over time, as the star spins down, these vortices must migrate outward to reduce the rotation rate of the superfluid. However, they can become pinned to nuclei in the crustal lattice or to defects in nuclear pasta. Pinned vortices cannot move freely, so the superfluid retains a higher rotation rate than the crust. A lag builds between the angular velocity of the superfluid and that of the solid crust. When the stress exceeds the pinning force, a large number of vortices suddenly unpin and move outward. The angular momentum they carry transfers to the crust, spinning it up abruptly. The observed glitch is this sudden transfer of angular momentum from the interior to the outer layers. Glitches vary in size and frequency. Some pulsars, like the Vela pulsar, show regular large glitches roughly every few years, while others display smaller or less predictable events. The magnitude of a glitch, often 1 part in a million of the total spin, may seem tiny, but given the immense moment of inertia of the star, the absolute change is enormous. The regularity of glitches in certain pulsars suggests that the process of vortex unpinning and repinning follows a statistical pattern influenced by the structure of the crust and the density of pinning sites. After a glitch, the star often undergoes a recovery phase. The spin frequency relaxes gradually back toward the trend of long-term spin down. This recovery reflects the re-equilibration of the superfluid and crust, as vortices repin and stresses rebuild. The details of recovery curves provide information about the strength of coupling between layers and the viscosity of the normal components. Some recoveries show multiple timescales, indicating that different regions of the star contribute. These observations help map how superfluid and crust interact in different density regimes. Star quakes are another manifestation of stress release. The crust of a neutron star is solid and can support strain, but as the star cools and spins down, the equilibrium shape changes. Rotation makes the star ablate, but as spin slows, the equilibrium shape becomes more spherical. The rigid crust resists this change building strain until it fractures. When a starquake occurs, the crust shifts abruptly, releasing energy. This can change the distribution of the magnetic field and alter the pulse profile. In magnetars, starquakes are thought to trigger giant flares, bursts of X-rays and gamma rays that release more energy in seconds than the Sun emits in a year. The link between starquakes and glitches is still under discussion. In some models, a starquake can trigger vortex unpinning, leading to a glitch. In others, glitches occur primarily through vortex dynamics without crust cracking. The coexistence of both processes suggests that neutron stars may experience a combination of mechanical and superfluid stress release depending on conditions. Magnetars provide compelling evidence for crustal involvement since their bursts are clearly linked to magnetic and mechanical stresses in the outer layers. Glitches have practical importance beyond their role in dense matter physics. They must be accounted for when pulsars are used as precision clocks. In pulsar timing arrays, where networks of pulsars are monitored to detect gravitational waves, glitches introduce timing irregularities that complicate analysis. Understanding the physics behind glitches helps astronomers model and correct for these events, preserving the utility of pulsars as cosmic laboratories. Statistical studies of glitches reveal patterns. Large glitches tend to occur in younger pulsars with higher spin-down rates, while older millisecond pulsars show fewer or smaller glitches. This trend suggests that crustal and superfluid dynamics evolve with age. In young stars, stresses build quickly, leading to frequent large unpinning events. In older stars, reduced spin-down and weaker pinning forces make glitches rarer. These observations provide a chronological picture of how the interaction between superfluid and crust changes over millions of years. Theoretical work on glitches uses models of vortex dynamics, superfluid hydrodynamics, and crustal elasticity. Simulations attempt to reproduce the collective motion of billions of vortices interacting with a complex lattice. While the details remain challenging, broad features of the data are reproduced supporting the vortex unpinning model. Laboratory experiments on superfluid helium provide some analogies, though the densities and forces are far removed from those in neutron stars. These experiments nevertheless show that superfluids can store angular momentum in vortices and release it, suddenly lending credibility to astrophysical models. Observations continue to refine the picture. High-precision radio timing allows measurement of glitch amplitudes and recovery phases in great detail. X-ray monitoring of magnetars provides evidence of coincident bursts and glitches linking interior and magnetospheric activity. Future instruments with greater sensitivity may detect gravitational waves from sudden rearrangements of the crust during starquakes, providing a new channel of information. Glitches and starquakes demonstrate that neutron stars are not static objects but dynamic systems where stresses accumulate and release. They show how quantum mechanical states of matter such as neutron superfluidity manifest on macroscopic scales. They also illustrate the role of the crust as both a rigid shell and a participant in the star's rotation. Every sudden jump in frequency or burst of high-energy radiation carries the imprint of interior processes occurring under conditions beyond laboratory reach. The continued study of glitches enriches both astrophysics and fundamental physics. By recording the timing of pulses with microsecond accuracy, astronomers can probe how vortices move in a superfluid hundreds of light-years away. By watching bursts from magnetars, they can infer the breaking strain of matter compressed to densities billions of times greater than water. Glitches and starquakes thus serve as natural experiments, revealing the mechanical and quantum properties of matter under extremes unmatched elsewhere in the universe. The thermal evolution of a neutron star is governed by its ability to lose energy through radiation and to transport heat from the interior to the surface. Right after formation in a supernova, the newborn neutron star is extremely hot, with temperatures of billions of degrees. This heat does not remain for long. Within minutes to hours, the star cools by emitting neutrinos, elusive particles that carry energy away almost without interacting. Unlike photons, which can be trapped by the dense matter, neutrinos escape freely, making them the dominant cooling mechanism during the first 100,000 years of the star's life. The outer core is the principal site of neutrino production. The modified Urca process operates when a neutron transforms into a proton, an electron, and an antineutrino, or the inverse reaction where a proton captures an electron to form a neutron and a neutrino. A bystander nucleon is required to conserve momentum, hence the term modified. This process is slower than the direct Urca process but is always allowed. The direct Urca process, where no bystander nucleon is needed, is far more efficient, but requires a high fraction of protons to conserve momentum. Whether direct Urca operates in a given neutron star depends on the density and composition of its core. If it does, cooling is dramatically accelerated. Observationally, only a subset of neutron stars show evidence for such rapid cooling, implying that direct Urca is allowed only in the most massive stars. Neutrino emission also arises from Cooper pair formation and breaking. When neutrons or protons in the core condense into superfluid or superconducting states, pairs form and break continually. Each time a pair forms a neutrino and an antineutrino are emitted, this process produces a burst of neutrino emission as the critical temperature for pairing is crossed. The rapid cooling observed in the neutron star within the Cassiopeia, a supernova remnant, is interpreted as evidence for the onset of neutron superfluidity in its core, with neutrino emission from pair formation accounting for the sudden temperature drop. Beyond neutrinos, photon emission from the surface becomes the main cooling mechanism at later times after about 1 million years. The surface temperature during this stage is in the range of hundreds of thousands of degrees, producing X-ray emission detectable by space telescopes. The surface temperature depends not only on the total internal energy, but also on how heat is transported through the crust and outer layers. The thermal conductivity of the crust, determined by electron scattering off nuclei and impurities, sets the efficiency of this transport. A pure lattice allows heat to flow easily, while an impure lattice slows conduction and creates temperature gradients. Observations of surface temperatures therefore provide indirect constraints on the composition and order of the crust. Accretion in binary systems modifies thermal evolution significantly. When matter falls onto a neutron star from a companion, it deposits heat deep in the crust. Compression of the crust by fresh material triggers nuclear reactions such as electron captures neutron emissions and pycnonuclear fusion. These reactions release heat, a process known as deep crustal heating. When accretion halts, the crust cools back toward equilibrium with the core. Monitoring the cooling of transiently accreting neutron stars has become a powerful probe of crustal properties. The timescale and shape of the cooling curve reveal the thermal conductivity, heat capacity, and possible superfluid effects within the crust. Magnetic fields also influence cooling. In magnetars, the magnetic field strength is so high that it alters the opacity and conductivity of the surface layers. Heat can flow more readily along magnetic field lines than across them, leading to anisotropic surface temperatures. This produces hot spots at the magnetic poles and cooler regions elsewhere. Observations of pulsed X-ray emission from magnetars confirm such uneven temperature distributions. The magnetic field also decays over time, releasing energy that can reheat the star. This internal heating counteracts cooling and may explain why magnetars remain hotter than expected for their age. Neutrino processes involving exotic particles could further affect cooling if such particles exist in the core. If hyperons or deconfined quark matter are present, they open new neutrino channels that accelerate cooling. However, the absence of widespread rapid cooling among observed neutron stars suggests that these channels are either suppressed or only present in stars above a certain mass. By comparing observed thermal histories with model predictions, astronomers constrain the presence of exotic matter in the inner core. Theoretical models of neutron star cooling are compared against data points from observed stars of different ages. Young cooling neutron stars observed in supernova remnants provide data at ages of hundreds to thousands of years. Middle-aged stars seen as isolated X-ray sources provide points at tens of thousands to millions of years. Older pulsars detected mainly in radio often lack measurable thermal emission, indicating they have cooled below detection limits. The overall agreement between models, including neutrino emission, crustal conductivity, and surface radiation, and the observed distribution of temperatures lends confidence to the current understanding, though uncertainties remain. The study of thermal evolution requires accurate treatment of general relativity. Heat transport equations and neutrino emissivities must be calculated in curved spacetime, and redshift corrections must be applied to connect interior temperatures with surface observables. Despite the complexity, modern simulations incorporate these effects and produce predictions that can be directly compared with telescope data. Space missions such as Chandra, XMM, Newton, and NISA have been central in providing the necessary observations. In addition to isolated stars, accreting systems provide laboratories for extreme thermal physics. Repeated cycles of accretion and quiescence test the heat capacity and thermal conductivity of the crust. Bursts of thermonuclear burning on the surface known as X-ray bursts heat the outer layers and alter subsequent cooling. By comparing observations of multiple systems, astronomers piece together a consistent picture of how neutron stars manage their heat. Thermal evolution therefore serves as a diagnostic tool for the physics of dense matter. The cooling rate reveals whether neutrino processes such as direct Urca or exotic particle channels are active. The cooling of accretion-heated crusts constrains conductivity and composition. Temperature anisotropies test the role of magnetic fields. Together, these observations map out the interplay of fundamental forces under conditions far beyond laboratory reach. Magnetic fields in neutron stars reach strengths unparalleled elsewhere in the universe. Typical pulsars have fields around 10 to the power of 12 Gauss, while magnetars can exceed 10 to the power of 15 Gauss. For comparison, the strongest steady fields produced in laboratories on Earth reach only tens of thousands of Gauss. The origin of such immense fields lies in flux conservation during stellar collapse. When the core of a massive star shrinks from thousands of kilometers to about 10 kilometers in radius, the magnetic flux is compressed, amplifying the field by many orders of magnitude. Additional dynamo action during the proto-neutron star phase may further strengthen the field. These fields shape the environment outside the star and penetrate its interior. In the magnetosphere, charged particles are forced to spiral along magnetic field lines, producing beams of radiation. At the surface, the field determines how heat is transported because conduction is easier along field lines than across them. Deep inside, magnetic stresses influence the structure of the crust and possibly the core. The presence of proton superconductivity means that magnetic flux is quantized into tubes which can interact with neutron vortices. These interactions may contribute to timing irregularities such as glitches. In magnetars, the field strength is so high that magnetic pressure can rival or exceed material pressure in the crust. This stress can fracture the crust, leading to star quakes. When the crust yields, magnetic field lines can reconnect, releasing stored magnetic energy. The result is a flare of X-rays and gamma rays, sometimes so powerful that it can be detected from across the galaxy. Giant flares have been observed only a few times, but their luminosities are extreme, confirming that magnetars hold vast reservoirs of magnetic energy. Magnetic reconnection is thought to operate in magnetoflares, much as it does in solar flares, but at far higher energy scales. Twisted magnetic fields become unstable, break, and reconnect, releasing energy into accelerated particles and radiation. The timescales of rise and decay in magnetar bursts match models of reconnection in ultra-strong fields. Observations with satellites such as Fermi and Swift have provided detailed light curves of these events, allowing comparison with theoretical models. The decay of magnetic fields also influences neutron star evolution. Strong fields decay more rapidly, both by ohmic diffusion and by Hall drift processes governed by the conductivity of the crust. As the field decays, it heats the crust, prolonging thermal emission. This explains why magnetars, despite being thousands of years old, remain much hotter than ordinary pulsars of similar age. Field decay is therefore not only a magnetic phenomenon, but also a thermal one. Coupled models of magnetothermal evolution are required to reproduce observations. At lower field strengths, ordinary pulsars show much slower decay. Their fields may persist for millions to billions of years with little change. However, in accreting systems where matter from a companion star flows onto the neutron star, the magnetic field can be buried beneath accreted material. This reduces the observable field at the surface and allows the star to be spun up to millisecond periods. Thus, magnetic evolution depends strongly on environment as well as on initial conditions. Magnetic fields affect radiation in subtle ways. At field strengths above about 4 × 10 to the power of 13 Gauss quantum electrodynamics predicts that the vacuum itself becomes birefringent, meaning that it alters the polarization of light passing through. This effect, called vacuum polarization, changes how photons propagate in magnetar magnetospheres. Recent X-ray polarimetry observations have begun to test these predictions, offering direct evidence of quantum processes in ultra-strong fields. The structure of magnetic fields inside neutron stars is not fully known. Models suggest that stable configurations require a combination of poloidal and toroidal components, meaning fields that loop from pole to pole, and others that circle around the star's equator internally. Purely poloidal or toroidal fields are unstable. The exact ratio and geometry determine how the field evolves and how stresses are distributed in the crust. Observationally, pulse profiles and spectra provide indirect hints of geometry, but detailed mapping remains beyond current capability. Interactions between magnetic fields and superfluid vortices in the core are another frontier. If neutron vortices pin strongly to flux tubes, the motion of vortices is hindered, affecting spin-down and glitch behavior. If they cut through flux tubes, mutual friction generates heat and alters angular momentum transfer. The degree of pinning versus cutting remains uncertain, but it is likely crucial for explaining the diverse glitch behavior across pulsars and magnetars. Theoretical studies use magnetohydrodynamics extended with superconductivity and superfluidity to model field behavior. Simulations show that strong fields can redistribute themselves over thousands of years through Hall drift, forming localized bundles of magnetic flux. These bundles may create localized heating and explain hotspots observed in X-ray images of magnetars. Ohmic diffusion, though slower, eventually dissipates magnetic energy, but in dense crustal regions it can be accelerated by impurities or pasta phases, Magnetic stresses in the crust set the stage for crust yielding. When stresses exceed the breaking strain, fractures occur. The breaking strain of the crust is believed to be high, among the strongest of any material, but even it cannot withstand the stress of magnetofields indefinitely. When failure occurs, magnetic reconnection follows, producing bursts. These bursts vary from short events lasting milliseconds to giant flares with tails that persist for hundreds of seconds. The pattern of bursts is thought to depend on how magnetic energy is stored and released in the crust and magnetosphere. The strongest magnetic events may also excite oscillations in the star. Quasi-periodic oscillations observed in the tails of giant flares are interpreted as global seismic vibrations of the crust and possibly the core. These oscillations provide a seismology of neutron stars, much like earthquakes reveal the structure of Earth. By analyzing the frequencies of oscillations, astronomers hope to probe crust thickness composition and magnetic coupling. Magnetic fields influence not only transient activity but also long-term evolution. The breaking of pulsar rotation arises from magnetic dipole radiation, where the rotating field radiates energy. The rate of breaking determines the pulsar's trajectory in the period versus period derivative diagram, a tool used to study populations of pulsars. Magnetars occupy the upper right with long periods and rapid spin down, while millisecond pulsars occupy the lower left with short periods and little spin down. The spread of objects across this diagram reflects differences in magnetic field strength and evolutionary history. The study of neutron star magnetism therefore links microscopic quantum effects to galactic scale observations. Fields stronger than any laboratory can produce control, the emission of pulses, the occurrence of flares, the cooling of stars, and the timing of rotation. They shape the crust and influence the core. By measuring timing, spectra bursts, and polarization, astronomers reconstruct the properties of magnetic fields and refine models of their origin and decay. In doing so, they explore the most extreme magnetic environments known in the cosmos. Observations provide the main pathway to constrain the physics of neutron star interiors. Because direct experiments at such densities are impossible, astronomers must rely on signals that emerge from the surface or from astrophysical events. Mass and radius measurements are central as they connect directly to the equation of state that governs how matter responds to compression. A precise determination of both mass and radius can rule out many theoretical models, since each equation of state predicts a distinct relation between these quantities. Over the past decades, advances in radio timing, X-ray astronomy, and gravitational wave detection have gradually narrowed the range of possibilities. Mass measurements come most reliably from binary systems. When a neutron star orbits a companion, the orbital motion can be measured through timing of pulses or through spectroscopy of the companion. In double neutron star systems or pulsar white dwarf binaries, the exquisite regularity of pulsar signals allows precise determination of orbital parameters. Relativistic effects such as periastron advanced gravitational redshift and Shapiro delay provide additional constraints. Several neutron stars have been measured with masses around 2 times that of the Sun. These massive stars demonstrate that the equation of state must be stiff enough to support such weight without collapse, ruling out models with excessive softening from hyperons or exotic phases. Radius measurements are more challenging. They require observations of thermal emission from the surface, often during periods of quiescence when accretion has ceased, or from isolated cooling neutron stars. The observed spectrum corrected for gravitational redshift and atmospheric effects can yield a radius estimate. Instruments such as the Neutron Star Interior Composition Explorer, mounted on the International Space Station, use X-ray pulse profile modeling to extract radius information. By measuring how hot spots on the surface appear as the star rotates and accounting for light bending in strong gravity. NICER constrains both mass and radius simultaneously. Results to date suggest radii around 11 to 13 kilometers for stars of about 1.5 solar masses. These measurements provide strong limits on the equation of state favoring models of intermediate stiffness. Gravitational wave observations from mergers have opened a new window. The event GW1817, the first binary neutron star merger detected in 2017, produced a signal that included information about tidal deformability. As two neutron stars spiral together, each is distorted by the gravity of the other. The amount of distortion depends on the internal structure, and thus on the equation of state. A stiff equation of state produces stars that are larger and more easily deformed, while a soft equation of state produces smaller, less deformable stars. Analysis of GW170817 constrained tidal deformability to moderate values, ruling out extremes and supporting the intermediate radii found by NICER. Future detections with improved sensitivity will refine these constraints further. X-ray bursts and cooling curves also provide indirect evidence. In low mass X-ray binaries, accreted material builds up on the surface until it undergoes unstable thermonuclear burning, producing bright bursts. The shape and decay of these bursts depend on the surface gravity and radius. Observations of cooling tails from bursts allow estimates of radius that complement NICER results. Similarly, monitoring the cooling of young neutron stars in supernova remnants provides information about interior composition. If rapid cooling channels such as direct Urca processes were active in all stars, observed temperatures would be much lower. The fact that most stars cool more slowly suggests that only some stars, likely the more massive ones, allow rapid processes. Magnetar activity provides another probe. The occurrence of giant flares and bursts reveals how strong magnetic fields interact with the crust. The frequency and energy of bursts depend on the breaking strain of the crust and the geometry of the magnetic field. Quasi-periodic oscillations detected in flare tails may correspond to seismic vibrations of the crust or global modes involving the core. By comparing observed frequencies with theoretical models, researchers attempt to extract information about crust thickness, composition, and magnetic coupling. Although uncertainties remain, magnetar seismology represents a promising avenue for probing interiors. Timing irregularities such as glitches also act as observational probes. The size and distribution of glitches inform models of superfluid vortex pinning and motion. The post-glitch recovery reveals coupling strengths between different regions of the star. Statistical studies across many pulsars show trends with age and magnetic field, providing clues about how interior dynamics evolve. Each glitch is a small experiment conducted by nature, and long-term monitoring accumulates a data set that constrains models of superfluidity and crustal structure. Polarization measurements are a newer tool. X-ray polarimetry, pioneered by recent missions, can detect the orientation of photon electric fields as they leave the magnetized surface. Polarization patterns depend on magnetic field strength, geometry, and quantum electrodynamics effects such as vacuum birefringence. By measuring polarization, astronomers can test theories of ultra-strong field physics and indirectly constrain conditions near the surface. Although this probes the outermost layers rather than the core, the information feeds back into global models of field evolution and magnetothermal coupling. Gravitational wave astronomy promises to expand the dataset further. Continuous waves from rotating asymmetric neutron stars, though not yet detected, would provide direct measurements of crustal strain and interior viscosity. Post-merger signals from binary collisions may reveal whether the remnant briefly survives as a hypermassive neutron star before collapsing into a black hole. The lifetime and oscillations of such remnants depend sensitively on the equation of state. With improved detectors, these signals could map the behavior of matter at densities unreachable by any other means. All these observational channels converge on the same goal, constraining the relation between pressure and density at extreme conditions, by combining mass-radius tidal deformability. Cooling bursts, glitches, and polarization. Astronomers triangulate the true equation of state. Each observation rules out some models and supports others. The convergence of independent measurements toward intermediate stiffness provides growing confidence, though uncertainties remain, especially regarding the possible existence of exotic phases in the inner core. The future holds promise of sharper answers. Next-generation X-ray missions aim to measure pulse profiles with higher precision. Gravitational wave detectors will gain sensitivity to both in-spiral and post-merger phases. Radio arrays monitoring pulsars will continue to refine timing stability. Together, these instruments will push constraints to a level where competing equations of state can be distinguished clearly. Step by step, the combination of observation and theory brings the interior of neutron stars into sharper focus, turning them into laboratories for fundamental physics that no experiment on Earth can replicate. When two neutron stars orbit each other in a binary system, their gradual in-spiral and eventual collision provide some of the most dramatic laboratories for dense matter physics. The in-spiral is driven by the emission of gravitational waves which carry energy and angular momentum away from the system. As the stars spiral closer together, the frequency of the waves rises until merger. The waveform encodes information about the masses and tidal deformabilities of the stars which reflect the stiffness of matter in their interiors. The first detection of a binary neutron star merger in 2017 confirmed decades of prediction and opened a new field of multi-messenger astronomy. During the late stages of in-spiral tidal forces distort each neutron star. The extent of this deformation depends on how easily the star's interior can be stretched, which in turn depends on the equation of state. A stiff equation of state produces stars with larger radii that are more deformable, while a soft equation of state produces compact stars less affected by tides. These deformations change the phase of the gravitational wave signal. By analyzing the waveform, scientists extract constraints on tidal deformability and therefore on the internal pressure at several times nuclear density. The limits derived from GW170817 ruled out some very stiff and very soft models, supporting an intermediate stiffness consistent with X-ray measurements. When merger occurs, the outcome depends on total mass and the equation of state. If the combined mass is above the maximum supportable by pressure collapse to a black hole, happens quickly within milliseconds. If the mass is lower, the remnant may survive briefly as a hypermassive neutron star supported by differential rotation and thermal pressure. Such remnants oscillate violently, emitting gravitational waves at kilohertz frequencies. These post-merger signals contain information about the high-density equation of state, but current detectors lack sensitivity at these frequencies. Future observatories may capture them, providing direct probes of the inner core where uncertainties are greatest. Mergers are also sites of heavy element production. When neutron-rich matter is ejected during collision, rapid neutron capture, or our process, builds up elements heavier than iron, including gold, platinum, and uranium. The electromagnetic counterpart of GW1787, known as a kilonova, was observed across the spectrum. Its light curves matched models of radioactive decay of our process elements. This confirmed that neutron star mergers are a major, if not dominant, source of heavy elements in the universe. Thus, studying the interiors of neutron stars is not only a question of dense matter physics, but also of cosmic chemical evolution. The amount and composition of ejecta depend on the structure of the stars just before merger. If the crust is thick and stiff, tidal tails can strip more material. If the equation of state is soft, stars are more compact and less matter may be ejected before collapse. Observations of kilonova brightness and spectra therefore feed back into constraints on the equation of state. In this way, gravitational waves, gamma rays, and optical light combine to probe physics at densities otherwise unreachable. Accreting systems also highlight the role of mergers. In some binaries, matter from a companion flows steadily onto the neutron star, altering spin and magnetic field. Over long timescales, this recycling produces millisecond pulses. But in double neutron star systems, the spiral inexorably leads to merger. Timing of pulses in such binaries measures orbital decay exactly as predicted by general relativity, confirming gravitational wave emission decades before direct detection. These systems remain natural laboratories for testing gravity and dense matter simultaneously. The remnant of a merger is not static. If a hypermassive neutron star survives briefly, it may emit intense neutrino radiation and drive winds that alter the composition of ejecta. Magnetic fields wound up during merger can reach extreme values, powering relativistic jets. Observed short gamma ray bursts are thought to arise from such jets launched after mergers. The central engine, whether a black hole or a rapidly rotating neutron star, determines the burst structure. In either case, the interior physics of neutron stars influences the observable universe on cosmological scales. Gravitational wave signals from mergers also provide information on the maximum mass of neutron stars. If a remnant collapses quickly, it implies the maximum mass is not much larger than the observed binary components. If it survives longer, the maximum mass must be higher. Combining data from multiple mergers will narrow the range of possible maximum masses, constraining the Tolman-Oppenheimer-Volkoff limit and therefore the high-density equation of state. Another observational channel is neutrinos. While none have yet been detected from neutron star mergers, models predict intense neutrino emission during the hot post-merger phase. Future neutrino observatories may capture these signals, adding another layer of constraint on temperatures, densities, and composition. In supernovae, neutrinos already provide direct information from collapsing cores. Extending this to mergers would complete the multi-messenger picture. In addition to binary neutron star mergers, collisions between neutron stars and black holes offer insights. In such systems, whether a neutron star is tidally disrupted before crossing the event horizon depends on its compactness, which is set by the equation of state. If disruption occurs, matter is ejected, producing electromagnetic counterparts and process nucleosynthesis. If not, the neutron star vanishes silently into the black hole. Observations of such events add complementary constraints on radii and stiffness. Altogether, mergers and their remnants represent the extreme dynamic laboratories of neutron star physics. They bring together all aspects discussed in quieter isolated stars: the balance of pressure and gravity, the nature of the inner core, the role of superfluidity and superconductivity, and the evolution of magnetic fields. In the chaos of collision, these properties determine whether a remnant survives, how much matter is ejected, what elements are synthesized, and what signals reach Earth. Multi-messenger astronomy, combining gravitational waves, electromagnetic radiation, and eventually neutrinos, transforms these violent events into precise experiments testing dense matter physics. The interiors of neutron stars, normally hidden beneath kilometers of dense matter, are revealed indirectly through these collisions. Each waveform, each kilon of a light curve, and each burst adds to the collective effort to understand matter at densities beyond nuclear saturation. In this way, neutron-star mergers are not merely catastrophic events, but essential tools for advancing fundamental physics, linking quantum chromodynamics, nuclear interactions, and astrophysical observations in one continuous narrative.